Hi everybody, in this video, I am going to explain the evacuation procedure in a refrigeration system and cover some important points. We need to evacuate or vacuum any refrigeration system before charging refrigerant for two main reasons. First, to remove non-condensables like air or nitrogen from the system. If non-condensables are present when the refrigerant is charged, they will cause the high pressure to increase. This is one of the 8 faults in any refrigeration system, which a trained engineer must know how to diagnose. The second purpose of evacuation is to remove moisture from the system. Remember, removing air does not necessarily remove moisture, so one must be very careful when evacuating a system. Moisture is the enemy of any refrigeration system. The presence of moisture causes many problems, such as blockage of the capillary tube or TEV due to the freezing of moisture, oil contamination and reduced lubrication effect, contamination of synthetic oil and acid formation, production of hydrochloric acid in refrigerants containing chlorine atoms. Almost all refrigerants become corrosive when exposed to moisture for a long period of time. Therefore, the removal of moisture from the system is essential. Vacuum pressure is always stated in absolute terms because it goes below atmospheric pressure, making atmospheric pressure an important factor. Vacuum pressure must be measured with an accurate vacuum gauge, either dial type or digital. For dial type gauges, the atmospheric pressure must be set before evacuation. If starting from 1000 millibars, or 1 bar, the vacuum reading must be compensated for atmospheric pressure, as dial type gauges only measure gauge pressure. Some digital gauges, like this one, have a barometric sensor and automatically detect atmospheric pressure when turned on, starting the vacuum measurement from that pressure. Now I am going to explain why a compressor should never be used for evacuation. This illustrates the ambient temperature, and this shows the water vapor pressure at that temperature in inches of mercury vacuum. For this explanation, I will use inches of mercury as the unit of vacuum pressure. In this context, 0 inches of mercury represents atmospheric pressure, and 29.92 inches of mercury represents perfect vacuum, which cannot be achieved on Earth regardless of the vacuum pump used. Whatever pressure unit is used, the basics remain the same. Let's consider a piston compressor used for evacuating a refrigeration system. Piston compressors have a dead volume between the piston and the valve plate, limiting the vacuum pressure to no lower than 27 inches of mercury. While such compressors can remove air, moisture remains an issue. In contrast, a rotary compressor, lacking the dead volume of a piston type, can achieve a vacuum pressure of around 28 inches of mercury. Additionally, any compressor used for evacuation operates without fluid, leading to significant heat buildup and potential compressor failure. Moisture is effectively removed from a system at vacuum pressures below 29 inches of mercury at normal ambient temperatures. Therefore, using a compressor for evacuation does not effectively remove moisture, depending on ambient conditions. For evacuating a refrigeration system, only a double-stage vacuum pump should be used. Now I am going to explain why vacuum time increases when moisture is present. Water is the only liquid on Earth whose liquid density is more than 1,600 times greater than its vapor density. In simple terms, if 1 drop of liquid water evaporates, it creates a large volume of water vapor. Having said that, let's see why removing moisture takes longer. Here we have a water pressure and temperature chart. In the last column, I included the specific volume of water vapor. Specific volume is the reciprocal of density, so the unit is also reciprocal. Pay attention to the first row, which shows that water boils at 100 degrees Celsius at 1 bar pressure. The specific volume of water vapor at that pressure is 1.7 cubic meters per kilogram. This means that if 1 kilogram of liquid water evaporates at 1 bar pressure, the volume of vapor created will be 1.7 cubic meters. You can see that as pressure decreases, the specific volume increases, which occurs during vacuum. This means that the same 1 kilogram of liquid water, when evaporated at, say, 0.012 bar, will occupy a volume of 106 cubic meters. So, it takes a long time for the vacuum pump to remove this large volume of vapor. The figures mentioned here are just examples, and one must be very careful if liquid water is present in the refrigeration system. It will be very difficult, and in most cases, impossible to remove a large amount of water by vacuum. Now let's see how one can be sure that moisture is removed and the system is ready for charging using vacuum pressure. First, I am going to explain water vapor pressure. This is a temperature and pressure table for water. Water at 1 bar evaporates at 100 degrees Celsius. If you go to the top of a mountain, water will evaporate at a lower temperature because the atmospheric pressure is lower. So, when pressure decreases, the evaporation temperature also decreases. Now look at this table. It is the same table that shows the pressure at which water boils for any given temperature. Let me explain again what these numbers mean. For example, at 28 degrees Celsius, water evaporates when its pressure is 37.8 millibars, or at 10 degrees Celsius, water evaporates at 12.2 millibars. These are called water vapor pressure. Having said that, let's see what happens during vacuum. This chart represents vacuum pressure versus time. The vertical axis is pressure, and the horizontal axis is time. This line represents atmospheric pressure. When the system is under vacuum and non-condensables are removed, the pressure drops below atmospheric pressure. As long as the vacuum pump is running, the gauge shows the vacuum pump's pressure. When the vacuum pump is turned off, the vacuum gauge shows the system pressure. From this point, three things can happen. If after the vacuum pump is turned off, the pressure increases and reaches atmospheric pressure, it indicates there is a leak in the system. The smaller the leak, the longer it takes for the pressure to reach atmospheric pressure, and vice versa. If after the vacuum pump is turned off, the pressure increases but only reaches the vapor pressure at the ambient temperature, then there is no leak, but moisture is present. If after the vacuum pump is turned off, the pressure increases but remains significantly below the vapor pressure, then there is no leak and no moisture. Now, the system is ready for charging. In British Standard 378 Part 2, it is stated that evacuation of halocarbon or hydrocarbon systems prior to charging refrigerant shall be less than 270 pascals absolute. Let's see what happens when a large amount of water is present in the system. Assume there is a large amount of water in this pipe. The ambient temperature is 21 degrees Celsius, so the water temperature is also 21 degrees Celsius. Water vapor pressure at this temperature is 2,487 pascals absolute. This means that when the vacuum pump is started, the water will not evaporate until the pressure reaches 2,487 pascals absolute. Now the vacuum pump is on, non-condensables are removed, and the pressure reaches 2,487 pascals absolute. Now, water starts to evaporate and creates a large volume of vapor. The vacuum pump removes this vapor. When surface evaporation occurs, the water temperature drops and the water becomes colder because heat is removed for evaporation. So, the water gets colder and colder. Let's say the temperature of the water reaches 10 degrees Celsius and the pressure is 2,200 pascals absolute. The evaporation stops, and no more water vapor will be created because at 10 degrees Celsius, the vapor pressure is 1,228 pascals absolute. Therefore, the pressure remains at 2,200 pascals absolute until the water temperature increases to around 19 degrees Celsius. This is why, if a large amount of liquid is present, it will be practically impossible to remove it by vacuum, and it takes a very long time. Thank you for watching this video.